for a moment. I think there's one other person I saw in the waiting room. So, yep, there we go. Okay, excellent. So good evening or good morning, depending on which time zone you are in. Thank you very much for coming to this Q-Chem webinar, which is given by Manisha, who was one of our 2025 Summer at Q-Chem interns this past summer. We're really excited to have her here. A quick introduction to Manisha as we're sort of getting the webinar started. She is currently a PhD scholar in the Department of Chemistry at the Birla Institute of Technology and Science, Palani. She got her BSc from DAV College, Jalandhar, in 2017, and she got her MSc from Mata Gujari College, 2019. And then she joined Professor Prashant Manohar's group at Birla Institute of Technology and Science, Palani, that's where she's currently at. And her work right now is currently focusing on computational methods for accurate descriptions of strongly degenerate electronic states, including implementation of EOM couple cluster variants with singles, doubles, and full triples. She's made a large number of valuable contributions to the Q-Chem software over the past several years, including a lot of work with couple cluster and couple clusters with triples in particular. And as I mentioned previously, she also joined us in the Q-Chem office this past summer as one of our 2025 Summer at Q-Chem interns. So she visited our office in Pleasanton, California, where she continued the exciting research work that she has continued to work on after her return back to her research group at BIS Palani. So we're really excited to have her here today to talk about some of both the work that she worked on this past summer and her ongoing couple cluster work. And before I hand it over to her, a couple of quick housekeeping things. So if you have any questions throughout the duration of the webinar, that is excellent, and we're excited to answer them. But if you would post them in the chat or the Q&A at the bottom, then that would be good, because then we can do a Q&A section at the end once Manisha is done with her talk. And I think that's all the housekeeping related stuff. So without any further ado, go ahead and I'll hand it over to Manisha. Thank you.
Thank you, Shannon, for the nice introduction. Good evening all. I'm Manisha and I'm presenting Q-Chem webinar today on the topic recent coupled cluster developments in Q-Chem, and my research advisor is Professor Prashant Manohar. So the outline of this presentation starts with the choice of method, then implementation of different variants of EOM-CCSDT methods, followed by results. And in the end, I'll discuss the implementation of CCSD small t method, which was my project at Summer at Q-Chem. So starting from the bound stationary electronic states of molecules. So atoms and the molecules are the quantum system, which are bound by the stable interactions. Now, this bound wave function makes the balance between the attractive and the repulsive forces, and these properties are governed by the time-independent Schrodinger wave equation. Now, the Schrodinger wave equation is exactly solvable for the hydrogen atom, but if we are looking for the many electron system, it is untractable. So we are moving further toward the approximation. So where we are fixing the nuclei and during the electronic motion, because nuclei are much more massive. So this is nothing but the Born-Oppenheimer approximation, which gave us the electronic Schrodinger wave equation. And here we are interested in only the electronic part, but still the exact solution of many electron system is untractable, again, due to the non-separable term VEE. VEE is nothing but the repulsion term, electron repulsion energy, 1 by Rij. So this is the coupled term where the motion of the ith electron will depend on the position of jth electron. So now we need to go for the approximate solution. So here our we are starting our approximation method by introducing the Hartree-Fock method. So the Hartree-Fock method is nothing but, in this method, we are just taking a single Slater determinant and each electron is moving in the field of other. Each electron are moving independent in the field of other electron. So in Hartree-Fock, the electrons are in pseudo-interacting motion, where the electron knows there are other electrons, but they don't feel their instantaneous position, but they feel their average potential. So here, also in Hartree-Fock, it recovers 95 to 97% of exact energy, which is very good, but that 3 to 5% of that correlation energy is also important, because it is the order of hundreds of kilocalorie per mole, and it is typically the enthalpy of a reaction. So now we need to recover that missing correlation. So now we have to go beyond this Hartree-Fock method. There are some post-Hartree-Fock method one can go for. First is the configuration interaction method, in which we are just taking the linear combination of the excited determinants. If we add all the determinants, it will lead to the full CI results. But now, the full CI, the factorial scaling of full CI is very high. So we are moving to the truncated scheme. But if we use the truncated scheme using CI method, then it will lack the size extensivity and the size consistency. So then we move to the other many-body perturbation theory, where the MP2 method is well known. It captures the dynamic correlation really well with a low cost. But when we are moving toward MP3, MP4, and so on, we are stepping up the ladder toward the accurate energies. But the scaling of this method is very high again. And sometimes we feel the convergence issues during dealing with the strongly correlated system. So another choice of method is the coupled cluster method. Among all these methods, our choice of method is the coupled cluster method. So here I have worked on the coupled cluster single, doubles, and triples. So I will be more talking about the CCSDT method. So the wave function of the coupled cluster is defined as psi naught e to the power t phi naught, where phi naught is the reference determinant, and most likely it is the Hartree-Fock determinant. Here we have truncated our t up to t3, where the t is equals to t1 plus t2 plus t3, where the t1 involves the excitation from the singles, and t2 involves excitation from the doubles, and t3 the excitations from the triple. Now we are substituting this coupled cluster wave function in the Schrodinger wave equation and multiplying by e to the power minus t operator to it, and it will lead to the similarity transformed Hamiltonian, which make it non-Hermitian in nature, and which only contribute to the connected terms, and the disconnected terms drop out and tends to zero, and we'll have the energy of the coupled cluster method. So here it is the most, the ground state coupled cluster method is the most efficient tool for the treatment of electron correlation effects for the closed shell system, and it captures the dynamic correlation really well. It is size extensive, and it is widely applicable for the calculations of correlation energies, molecular properties, gradients, and potential energy surfaces. Now, if we are looking for the states like excited, ionized, and electron attached states, or we are dealing with the system which is having the multi-configurational character, and also if we have the system which is having very small homo-LUMO gap. So for all these system and states, the single reference coupled cluster method do not respond well. So how we can handle those degeneracies and near degeneracies? Now we have to extend this method to to further the alternatives of coupled cluster method, that are the EOM-CC, MRCC, and CCLR. So here, among all these methods, our choice of method is EOM-CC method. So in this EOM-CC method, it is again a single reference method. So in which our reference state is always the ground state coupled cluster method, coupled cluster wave function, and we are exciting, let's say we are doing the computation for the excitation energy. So we are exciting it up to the kth state, and this linear operator is applied on this function, and it will for us, we have truncated this R operator up to R3 because we are working on CCSDT, EOM-CCSDT. Then again, we are employing this similarity transformed Hamiltonian. Again, it leads to the excitation, ionized, and electron attached energy, which is nothing but the difference between the energy at the kth state minus the energy at the reference state. So using EOM-CCSD method, EOM-CC method, we extend CC to access the near degenerate electronic states obtained by ionization, electron attachments, and the excitation. Now, the appropriate variants are chosen for the desired type of electronic state, such as IP, EA, EE, SF, DIP, and DEA. So here we are presenting the excitation operator for the variants of EOM-CC methods. So different target states can be accessed by this reference states and EOM operators. So here we are choosing the EE reference. So this is the N electron reference, and we are applying the excitation energy operator on it, and it will lead to the low spin states. And we can see that the spin is conserved in the reference in the target state, in the target. So we can see that in the reference and in the target state, the spin is always singlet. In case of and also we can have this this kind of excitation here in EE, but this contribution is from the doubles, and we haven't add all these excitations here because I'm saving some space here. So now discussing about SF states, we have to take the high spin reference here in the target state. It by applying the spin flip operator, we are getting this couple of target states, which are low spin states. And here we can see that our reference is the triplet, and it will turns to the low spin state in the target states. So in EA, we are having the N electron system, and we are employing the EA operator on it, and it will lead to the N plus 1 target state. So here, this configuration is from doing EA alpha, and this configuration will get by doing EA beta. So there are specific keywords in the Q-Chem. If we do EA, we can specify this keyword EA alpha to get the alpha electron here in the in this state. And in case of beta, if we want beta electron here, so we can use this keyword EA beta. In case of IP, so we are using the N electron reference, and we are employing the IP excitation operator. So it will reduce 1 electron. So in our target state, we'll having N minus 1 electrons. So here we have started from the N electron reference, and it will tend to the N minus 1 electron reference. So here in both these states, we are presenting the IP beta only, but one can go for IP alpha. But by default in Q-Chem, it will remove for IP, it will remove the beta electron only. So if anyone is interested in removing the alpha electron, we can also give the keyword IP alpha. So in the DEA states, we are having the N electron systems, and we are employing the DEA operator on it, and it will lead to the N plus 2 electron system. Whereas in DIP, we are having the n electron reference, and by employing the DIP operator on it, it will give us n minus 2 electron reference. So here, the specific EOM-CC model will have the choice of excitation levels in T and R, and the choice of a reference and the type of R really matters. So this presentation, this slides presents the diagrammatic skeletons of R1, R2, and R3. So here we are presenting our R for different variants of EOM-CCSDT method for the SF, DIP, DEA, IP, and EA. So for SF and EE, the programmable expressions remain same for the R1, R2, and R3. But in case of spin flip, there is change in the spin projection by 1 unit. So that is the only difference between EE and SF. We have to take the high spin reference, and it will the spin flip operator will change the spin by the by spin projection by 1 unit. So here we are presenting the DIP and the DEA states as well. So in principle, it should be R2, R3, and R4, but in our case, we are presenting it R1 plus R2 plus R3 because we are counting the index. So it is one body part with the 2 index, and R2 is the 2 body part with 4 index, and R3 are the 3 body part with the 6 index. So here we have written it in that format, R1, R2, and R3 for both DIP and DEA. So here we are presenting the methods, electrons, and the R1, R2, and R3. So here in the EE, we have no change in the electron. So we are starting from the n electron reference, and in the target state, we are getting the n electrons. And in the spin flip, again, there is no change in the electrons. We are starting from the high spin reference and with an electron, and in the target state, we are getting the an electron with the low spin states. And in DIP, we are removing 2 electrons. And 2 electrons. In IP, we are removing 1 electron, and in EA, we are adding 1 electron. So when we are removing 2 electron, it will generate 2 holes for R1, and it will generate 3 holes, 1 particle formulation, and again for R3, it will have the 4H and 2P formulation. So similarly, we can write it for DEA, IP, and EA. So here the motivation toward triples was for spin flipping, double ionization, and double electron attached states. The EOM method has been explored with singles, doubles, for singles and doubles, but for the high precision based calculation where the homo-LUMO gap reduced to 0.1 electron volt, there the variants of EOM-CCSD is not sufficient for the correct reliable computation. So introducing triples will enhance the accuracy and improves the trends in the states. And also the computational scaling of these coupled cluster methods are very high, which limits the applicability of the system. By introducing the frozen natural orbital schemes can widen the applicability of this method to the bigger systems. So we have tested the FNO for the energies and the energy gaps. So there is also the lack of systematic studies of accuracy versus the cost trade-off, and there is no quantitative benchmarking studies for the energy deviation versus the computational saving. By introducing the cost-effective techniques to EOM variants, we can further study the accuracy versus the cost trade-off. So here in this slides, we are presenting our implementation. So we have developed the CCSDT and the EOM-CCSD energy codes within the Q-Chem. We have starting from the scratch from CCSDT ground state method. Then we went for the equation of motion, coupled cluster, single, doubles, and triples method for the excited state. So first we have developed the EOM-CCSDT, then we went for the spin flipping part, and then we have implemented the ionization potential and the electron attachment, and at last we have implemented the double ionization potential and the double electron attachment. So here our new development, new implementations of methods are SF EOM-CCSDT and DIP EOM-CCSDT and DEA EOM-CCSDT. As the scaling of CCSDT and EOM-CCSDT is n to the power 8, so we have also worked on the cost-effective technique, that is the use of the frozen natural orbital. So these above features are available in Q-Chem 6.1 to 6.3 released versions. So here in this slide, we are presenting the vertical excitation energies of CH radical. But before going to the vertical excitation energies, let us briefly talk about the frontier molecular orbital diagram of CH radical. So here we are presenting the frontier molecular orbital, that is the sigma star and these two-fold degenerate pi orbitals. In the EE reference, the ground state is the 2 pi, where there is a non-uniform filling of these electrons, and when we are applying the excitation operator to it, and it will leads to it will break the degeneracy when it went to the excited state, and it will change the character of the state by delta. And yes, but here we can see that the spin is almost same. The spin in the reference and the excited state is the same. So in case of SF reference, we can see that there is uniform filling of the electrons, and it is having the reference the quartet sigma state, and then we apply the spin flip operator on it, and the degeneracies remain intact. But in the excited states, in the spin flip excited state, it will turns to the low spin state. From quartet, it will turns to the doublet state. So in the next slide, we are presenting the job structure of the CH radical. Now, this will talk about how to set up the EOM-CCSDT calculations for SF and the EE variants. First, we have to decide which EOM model we need, and we have to set up the reference appropriately. So for EE, the reference is 02, and for SF, the reference is 04. And again, we have to specify the number of target state. As the point group of the CH radical is C2V, so we have to specify these EE states according to the states which we want to target. And in SF, we have to specify those states for which we actually want to target, but we have to mind the symmetry. So the symmetry of the target state will equal to the irrep of the reference into the irrep of the transition. So one can also use the performance related keywords, that is the CC memory, frozen core, and the FNO. So here in this slide, we are now presenting the vertical excitation energies of the CH radical. So we have used this ground state, experimental ground state equilibrium bond length, and the single point computations were done using the CCPVTZ basis. So this table presents the UHF and the ROHF reference of EE and the SF method at the different levels of EOM theories. So here we can see that the vertical excitation energies for EE are overestimated with respect to SF. And to get the more clarity about these numbers, we have presented the truncation errors between the excitation energies and the spin flip energies for various truncation levels of EOM-CC methods. So here we can see from going from EOM-CCSD to CCSDT, we are converging the errors. So the errors are reducing when we are going from EOM-CCSD to CCSDT. So using UHF reference, the EOM-CCSD error is 1.403 electron volt, and it decreased to 0.042 electron volt for EOM-CCSDT. In the using the ROHF reference, we are having 1.292 electron volt of error at EOM-CCSD level, and it reduced to 0.038. And we have also checked the performance of the single precision algorithm with our double precision algorithm. It turns out to be really well for the energies and energy gap. So from here, from the table, you can see that we are not compromising with the accuracy, but we are getting the enhanced speed up by reducing the memory footprint by the factor of half and gaining speed up by the factor of 2. So here we are presenting the job structure of the methylene diradical. So in this job, what we are going to do is we are targeting the CH2 excited states, and we are taking different references, like we are taking the dianionic reference and we are employing the DIP operator on it, and it will give us the CH2 excited state, whereas we are taking the dicationic reference states and we are employing the DEA operator on it, and it will give us the CH2 excited state. And in case of spin flip, we are using the high spin reference and it will leads to the same CH2 excited state. So the purpose of doing this is we are using different variants to get the same excited state. So these are the job structure for the SF, DIP and the DEA. So here for SF, we are using the triplet high spin reference. For DIP, it is -2 charge, 1 multiplicity for DIP reference. And for DEA reference, it is 2 plus 2 charge, and the 1 is the multiplicity. So here we have worked on the energy part only. So we are describing our job type as SP only. Method is EOM-CCSDT. We have used the TZ2P basis, but one can use the other bases as well. So we have also we have used the n frozen core is equals to 0. So this says there is no freezing of the core orbitals, and here we have specified our spin flip states according to the states which we want to target. And here the maximum Davidson iteration we have set is 60. By default it is 60, and one can use the guess vector for singles if required. Similarly, we can give the RAM vectors for DIP and these DEAs. So here in the here we are presenting the vertical and the adiabatic excitation energies of the CH2 excited state. So here we can see that if we compare SF-CCSD with CCSDT, it will underestimate all the states, whereas if we compare DEA with DEA-CCSD with DEA-CCSDT, they are overestimated. And again, for DIP-CCSD and DIP-CCSDT, if we are comparing both these states, the DIP-CCSDT is overestimating to the DIP-CCSD. So here, so in this table, we are presenting the adiabatic excitation energy. So we have used the benchmark method as the full CI, and we are comparing our different variants like SF, DEA, and DIP with the full CI, and we can see that all the SF states are overestimated with respect to full CI in case of both CCSD and CCSDT. And in case of DEA, DEA, it is underestimating the A1 state, first A1 state, and again the B1 is also underestimating, and this other A1 state is also underestimating. So also we can say that DEA CCSD is also underestimating the full CI result, whereas DEA CCSDT for the A1 state it is overestimating, and for the B1 state it is underestimating, and for again this A1 state it is underestimating. And if we compare the DIP results, DIP CCSDT, it is underestimating. All the states are underestimating with respect to the full CI. Now here, from this table, we can we have presented the error bars of SF, DIP, and DEA state with respect to the full CI. So in case of CCSD, we are having 0.04 electron volt of SF energies, and it decreased to 0.01 electron volt when we are comparing our SF results with the full CI. So for CCSD, it is 0.04 electron volt, and it decreased to 0.01 electron volt for the CCSDT method. For DIP state, it for CCSD it is 0.2 electron volt, and it decreased to 0.02 electron volt. And the errors in DEA energies is 0.02 electron volt, and it decreased to 0.01 electron volt when we compare with the full CI. So here numerically we can say that SF and the DEA energies are more accurate, but if we see the DIP errors at CCSD and CCSDT level, it so at CCSD it is 0.2, and it is improved by 0.02 electron volt, which is very much the 10% we have improve our error. So here we are presenting the job structure for IP and EA. So here we are taking this reference, a diarrhetical reference, and we are targeting now. We are now here we are taking a single reference, same reference for IP and EA, and we are targeting different states. So here after doing IP alpha, we will get this target state, and doing EA beta, we will getting this target state. But here our reference is common. So we have taken the example of the O2 molecule. So O2 is stable in the triplet state, ground state triplet. So we are choosing it. We have choosing this reference, and then we have mentioned these REM variables. So here our method is EOM-CCSDT. One can go for single precision algorithm as well, and if anyone wants, then one can add the memory. For the performance based keywords, one can add the memory, and IP alpha will remove the alpha electron from the reference, and EA beta will add the beta electron from the reference. Unrestricted is equals to fall is we are using the UHF based reference, and the basis is CCPV-DZ. So this occupied whenever there is there is in Q-Chem sometimes there is some energy, we will not get the right energy for the we are not getting we are not targeting the right states. The energies are sometimes flipped, so we can apply this occupied so dollar occupied, so we can change the occupancy of those molecular orbitals so that we can target the right state for right reason. So here we are presenting the ionization potential and the electron attached states. So first we are presenting the ionization potentials. So here we are presenting the direct and the indirect method for the ionization potential. So For so we are choosing this diradical states, and we are doing the IP alpha on it, and it will give us this monoradical. Now this is the direct method for the IP alpha. Now how we can get the direct method for this state? So now we are choosing here the dicationic state and doing EA alpha on it, and again we are choosing the dicationic state and doing DEA triplet on it by taking the difference between the EA alpha, the dicationic EA alpha minus the dicationic DEA triplet. It will lead to the IP, this IP state. So similarly, we can do it for the EA beta. So here we are choosing this diradical state, and we are doing EA beta on it. It will add the beta electron in the reference, and this is the direct method to evaluate the EA beta. Now, if we want to go for the indirect method, we have to choose the dianionic reference, and by doing dianionic reference, we are employing the IP beta, which will remove the beta electrons, and also again we are choosing the dianionic reference by employing the DIP triplet, and it will DIP triplet, it will remove the 2 electron, and by taking the difference between this IP beta and the DIP triplet, it will lead to the EA with the indirect method. So here in this table we have presented the couple of examples which presents the direct and the indirect IP and the EAs, and we have also presented the relative errors and the maximum absolute error we have observed at for B2, which is 0.759 for at CCSD level, and at CCSDT level it reduced to 0.355 electron volt, whereas for EA the maximum absolute error for CCSD is 1.506, and it reduced to 0.046. So here this indicates that significant improvement with the inclusion in the triple confirms the CCSDT captures the missing correlation from the truncated CCSD. So now we are presenting the vertical and the adiabatic ionization potential for the ionization energies for the benzene. So here benzene has the pi star orbital, which are twofold degenerate in the neutral D6H symmetry. Upon ionization, the degeneracy lifted to D2H geometry, and we have this vertical ionized state, which is 2E1G, and we have the adiabatic ionized state, which is the relaxed, this is the 2B2G. So the vertical IPs, the partial triples method underestimate the vertical IPs because so here we can see that the partial triples method, it underestimate the vertical IPs. So here we can see that we can also say that the target is more correlated with respect to the reference, and so there is imbalance in the correlation, but by adding the full EOM-CCSDT, it improves by 0.02 electron volt, and it matches the experimental results better. Now we are here presenting the adiabatic IPs. For FTDT, it overestimates the IP. So and in CC23 it underestimates the IP, and only EOM-CCSDT gave the balanced correlation and the more reliable results. So compared to EOM-CCSD, it underestimates by 0.01 electron volt. So the CPU timings required for running this job is this, and we have used the one node with 32 threads for computing this calculation for the benzene. So here we are presenting the implementation of CCSD small t method. So from the full CCSDT, we are turning to the approximate triples method, and this method preserves key physics of the triple excitation, but it dramatically reducing the n to the power 8 computational burden. Among them CCSDT. So there are another approximate methods to the triples, but among them the CCSDT stands out as a compelling option, it capturing the most important parts of the triple space. And we can also say it's a generalized version of MRCC method within the single reference formulation. So we are using the number of determinants that differ from the formal reference determinant by the singles and the double excitation, and can now be included in the reference state space. In our implementation, singles and double excitations from the secondary reference determinant has been truncated to include only those that correspond to the triple excitation from the formal reference determinants. Now, in the full CCSDT method, we have this wave function where T1, T2, T3 presents the excitation operators, and these Ig key presents the occupied orbital, and the ABC are the virtual orbitals. So here the dagger is the creation operator, and this is the annihilation. So how the CCSD small t is different from the full CCSDT. So the wave function of CCSD small t is given as e to the power t, T1 plus T2. The T1 and the T2 excitation amplitude remains the same, but there is some change in the T3 dash. So we have mentioning here T3 as T3 dash because it is different from the triple excitation which was used in the full triples. So here T3 dash has the 4 inactive indexes, that is IJ, small a, b. So but one active pair, that is the big I and big A, where I and A are the active, occupied, and the virtual orbital. So the sum over IA indicates the sum of over all the selected singly excited determinants. So here the expression remains the same, but we where the T3 has introduced, we have to eliminate T3 and we have to add it as T3 dash. So T3 dash is nothing but this. So we have worked on these libraries, libemo, for creating the active space, and liblegacy, in which we have partitioning. We have analyzed the partitioning of that active space, and this work was done during the summer at Q-Chem internship. And in the libcc, we have write the programmable expression, and it was executed in the CCMan2, which is the CC suite. And we are almost implemented this method, but the testing is going on, and we are probably checking this feature in the next May release. And we the original project we have proposed was the double spin flip, and it is also the development and the coding part is also done for that project as well, and we are also testing that codes. And we are hoping that we'll check in that feature also in the May release. So I would now like to acknowledge my advisor, Professor Prashant Uday Manohar, for his continuous support and guidance, Professor Anna Krelov, Dr. Andrew Gilbert, Dr. Kaushik Nanda, Dr. Shannon Hawk, and Dr. Zinchen Finch, and the whole Q-Chem team, my lab mates and friends, faculty staff, Department of Chemistry, BITS Pilani, and my beloved family. Thank you.
Very nice. Excellent job. So yeah, It's been very cool to have you here with us over this past summer, and to see this project sort of progress from like its very beginnings to where it is now. So, um, does anyone have any questions? If you have any questions, you can post them in either the Q&A or the chat. You can take your pick. Okay. If no one else has any questions, can you go back a couple of slides to yeah, this one. So I'm just out of curiosity, and there may not be a standard answer to this, but do you know how much it reduces the scaling? Like what the scaling of CCSD little t is relative to CCSDT?
It is between n to the power 6 to n to the power 7.
Okay, cool.
It's in between, yeah.
Nice. So I was just curious. So yeah, thank you. And then, so we do have one question, which is, have you benchmarked your implementations against other open source code in terms of performance?
Yes, we have no, not with the performance, but we have benchmarked the existing codes like the EOM-EE codes with the Bartlett. So for the accuracy point of view, we have done the benchmarking, but yes, but the performance, how good it is running, I mean, the speeds, I haven't.
So in terms of timings, yeah. This makes sense.
Yes.
Okay, excellent. Thank you. And then we have another question, which is this method implemented on GPUs?
No.
Okay, that's what I thought the answer was. So maybe some exciting future work to be implemented by someone in the future. But yeah, I think the
Yes, my junior is also working on the CVS. Probably it will be there in the next release.
oh nice, awesome. I didn't realize you guys were working on CVS too. That's exciting. So excellent. And yeah, let's see, are there any other questions from the audience? Give it another second. Okay, well, so if you think of a question after we close the webinar and go, oh darn, I wish I'd asked that. There will be a forum thread on the Q-Chem Talk forum where you can post any follow-up questions that you might have for the team and or Manisha to answer. And then also this webinar recording will be posted on YouTube probably within the next week or so. And thank you again to Manisha for an excellent webinar and also for coming to visit us over the summer. It's been really cool to have you visit with us and see the project and the cool science that you've been doing. And then also thank you for your many contributions of couple cluster code to Q-Chem. So we really enjoy having all of these exciting new methods that you've been working on as part of our code base. So thank you so much for all your hard work and congratulations on a job well done.
Thank you so much. And thank you so much for inspiring.
Yeah, of course. Thank you so much for being here and working with us. So we really appreciate it. So, and thank you for an excellent webinar. So, all right. Have a wonderful rest of your day or rest of your evening, depending on time zones. And goodbye, everyone. Thank you.